I think it's really helpful to go over a specific example when we're doing these coordinate transformations and principal stresses and Mohrs. So this is the specific example that we added in class in response to your clear muddy papers. And in this case, I actually do have the angle that I intended for us to do, which is rotating 40 degrees counterclockwise. So this will be a little bit different than the one that you did in class, which I think is an additional good exercise. So we're given an original stress state, and this is typically how these things start, is that we have some sort of little cube of material. In this case, on our x-plane, we have 26.5 megapascals in compression. On our y-plane, we have tension pulling with 5.5 megapascals, and then we have a negative shear stress of 12 megapascals. So the first thing we're going to do is rotate the coordinate system 40 degrees counterclockwise about the z-axis. In other words, from x, we are going to rotate up 40 degrees. So here we're going to use the coordinate rotation equations that are in page 2 of your gap notes, and all that we need to do is plug in sigma x, sigma y, tau xy, and our 40 degrees for theta, which makes this 2 theta be 80 degrees. So here we have that work done, and what we can see is that our sigma x prime goes to negative 25.1 megapascals, our sigma y prime should be 4.1 megapascals, and our tau x prime y prime should be 13.7 positive shear megapascals. So if you need to take a minute, please pause the video and make sure that you know how to plug those in correctly. And note that our rotation was 40 degrees counterclockwise, so the thing that gets plugged in for 2 theta here is 80 degrees. And that is counterclockwise as defined in our system, that's positive, so that's why we have a positive 80 degrees plugged in for all of these. And if we're consistent with all of this, this should work out with our Mohr circle. The second thing that we're going to do is look at the principal stresses. So here's all of our equations for principal stresses, and we can do this independent of Mohr circle. So we have our equations here for sigma 1 and sigma 2. This is the center plus or minus the radius. So if we plug in all of our values there, being careful to keep our negative where we have compression, we have negative 10.5 as our center and 20 as our radius. So that works out to be sigma 1 of 9.5 megapascals. That's defined as the largest tension. Sigma 3, defined as the most compressive, is going to be negative 30.5 megapascals, and that leaves sigma 2 as 0. So again, I got these by plugging into these equations, saying, okay, negative 10.5 is the center. If we do negative 10.5 plus 20, we get 9.5 megapascals. Negative 10.5 minus 20, we get negative 30.5 megapascals. And we had no other information about our third plane, so we assume that everything is 0, and therefore our other principal stress is 0. Tau max in plane is just going to be equal to the radius, so that's 20 megapascals. We want to also check for tau max overall. In this case, our second or our 0 principal stress is contained in between the other two, so we expect those to be the same. But the equation for that tau max overall is our largest tensile minus our most compressive over 2, and so that does in fact work out to be the same as tau max in plane at 20 megapascals. And then we have our orientation, so tangent of 2 theta p is equal to 2 tau xy over sigma x minus sigma y. We plug those in. Again, we're very careful with our negatives here to make all this work out correctly. So that was a negative tau shown on that cube, and negative compressive sigma x, and so we get 2 theta p to be 37 degrees and theta p to be 18.4. That's positive, so we expect that it will be a counterclockwise rotation up from the x-axis. So let's check our Mohr circle and depict all this on Mohr circle, and then we'll come back to what the cubes look like. So here we have our Mohr circle where we're plotting tau versus sigma. Sigma positive on the right. Tau clockwise is up, counterclockwise is down. And again, that's because this has that extra letter in it, so it sinks to the bottom. So let's look at our original stress state. So originally, our x-plane was negative 26.5 and 12 clockwise. Let's just zoom up and look at the original cube one more time. So our original x-plane is 26.5 compressive and 12 in the clockwise direction. Our original y-plane is going to be 5.5 tensile and 12 going counterclockwise. So depicting that on the Mohr circle, our x-plane is negative 26.5 and 12 clockwise, which is above the axis. Our y-plane is 5.5 and 12 counterclockwise, which is below the axis. So this is our original stress state. So first of all, let's do that 40-degree counterclockwise rotation, and that's depicted in the kind of aqua color. So here in the real world, it was 40 degrees counterclockwise, so on Mohr's circle, it's going to be 80 degrees counterclockwise. So our x-plane goes approximately 80 degrees, and our new x-prime plane then is negative 25.1 and 13.7 counterclockwise. So that's consistent with what we found with the equations. And our new y-prime plane, so here was the original y, it goes on the Mohr's circle 80 degrees counterclockwise, and we end up at 4.1 tension and 13.7 clockwise. So all that's consistent with what we found. Now let's look at the principal stress state. So our x-plane is here, and we're going to rotate our x-plane through the smallest angle to the closest principal stress, which in this case is going to be principal stress 3, our most compressive at negative 30.5. So the angle that we're going to rotate through is this 2 theta p. Again, on the Mohr circle, it's 2 times the angle in real life. So 2 theta p, and this again is going to be then counterclockwise. So I always start with my x-plane, and I pick out the smallest rotation to the closest principal stress and base it off of there. So we solved for that 2 theta p should be 37 degrees counterclockwise, and in fact it is. So that would mean that the y-plane would go also 37 degrees counterclockwise to, trying to do too many things here at once, to our principal stress 1 at 9.5 megapascals. Okay, so then we have our rotation to our shear coordinate system, so I'm going to do that as well. So we have our shear max in plane and overall is 20 megapascals. And so here we have our x-plane. I'm going to, again, base this off the x-plane just because that's easiest for me. So for my x-plane to rotate down to the maximum shear, I'm going to keep it counterclockwise, and I'm going to say, well, I know that this original rotation was 37 degrees to the principal coordinate system, and then we have to go another 90 degrees to the shear coordinate system. So my pink angle, 2 theta s, is going to be that 37 degree rotation to the principal coordinate system plus another 90 degrees, which is going to be 127 counterclockwise. And yep, that looks like about 127. So my x-plane is going to rotate to normal stress of negative 10.5, and that's going to be all on both planes. And it's going to rotate to a 20 megapascal counterclockwise shear stress. All right, so let's try putting the rotations of these cubes next to our Mohr circle. So that's what I'm trying to do here for you. So let's map these on, and these should coordinate in terms of the color. So our rotation from our original coordinate system rotated 40 degrees counterclockwise. So here's 40 degrees counterclockwise, which is positive in terms of the equations, according to our definition that positive is up from the x-axis. And we see that our x-plane went to our x-prime plane, which is negative 25.1 and 13.7 counterclockwise. So here's negative 25.1 and 13.7 going counterclockwise. And then our y-plane rotated to y-prime, which was 4.1 and 13.7 clockwise. So here's 4.1, 13.7 clockwise. So everything's consistent. Our equations popped out that x-prime should be negative 25.1, y-prime should be 4.1, and our tau x-prime y-prime should be a positive 13.7, which is what we get. Let's look at our principal coordinate system depicted here in purple. So our original x-plane rotates theta p counterclockwise to our principal stress 3, which is negative 30.5. So over here, our x-plane rotates 18.4 degrees counterclockwise to our principal stress 3, which is negative 30.5. So that's leaving our principal stress 1 at 9.5 to be on our old y-plane. And we have our angle depicted here. Theta p is 18.4. Over here on the Mohrs circle, it's twice that, which is 37. This is counterclockwise. It's also positive in our equations as defined. And there are no shears because by definition there are no shears in the principal system. And then our last one is our max shear. So that's depicted here in the pink. So again, we had from the x-plane, it was rotating on the Mohrs circle 127 degrees counterclockwise. So in the real world, it's rotating from the x-plane 63.5 degrees counterclockwise. So that's this rotation. And what should be on this rotated x-plane? We should have a normal stress of negative 10.5. That's the center or the average value, and that should be on all the planes, and it is. And then what about the shear stress? So on our rotated x-plane, our shear stress should be 20 megapascals going counterclockwise. And we knew that because here on the Mohrs circle, we rotated through that 2 theta s from the x-plane counterclockwise, and we got a shear stress that was 20 megapascals counterclockwise. So over here, 20 megapascals going in the counterclockwise direction. So hopefully this is helpful to tie together the equations, the Mohrs circle, and the rotations on all of these cubes.